Okay, so now finishing our discussion on section 1.1, the random component in this foundational paper on generalized linear models. Again, the link to this paper and complete playlist where I'm going through each line of this paper will be provided in the description of this video. But right now we're basically just talking about these last three statements that you have here, where basically we are going to plug in alpha of phi equals 1 and see how that affects some of the equations we've already discussed. So starting with the exponential family distribution, notice that when alpha of phi equals 1, 1 is not a function of phi. So basically this exponential family will no longer depend on the parameter phi. All right, so let's go to the blackboard and I can kind of talk about this a little more in detail for each of the three equations. So when alpha of phi equals 1, I basically end up with this being 1. So 1 times anything is just itself, so I can just not write that. And then I have z of theta minus g of theta plus h of z. Now, this is no longer a function of phi, right? Because alpha of phi equals 1, which is not a function of phi. So basically, this becomes beta of z, right? H of z and beta of z can be absorbed together into just being h of z, which is why, we don't write it as two separate functions. You just basically, h will absorb whatever was there, and then you end up with what we see here. Okay. All right, for this second equation, this one will follow very directly from equation 3, where basically I'm going to plug in 1 here, and I get that the first derivative of the log likelihood with respect to theta is just going to be z minus mu, basically because you plug in a 1 right there. Okay, so that one's pretty straightforward. This last one, it uses both equations 4 and 5 to derive, to think through. So basically, we see on equation 5 that, when this is 1, this basically equals negative v, right? You move the negative to the other side, and you get what you see here. All right, and then that equals positive v. So let me write this. So when you move the negative to the other side, you get negative the second derivative with respect to theta equals positive v. Positive v right here. When this is 1, so this is 1 here, so we'll just equal the variance of z, right, which is what you see here. Okay, so you can see that basically these three equations, they follow pretty directly from everything that we've talked about previously. You're just plugging in 1 for alpha of phi.